On today's episode of Dakanta Chemistry, we're learning about polar bears. Not. We are learning about polar bonds, not polar bears, but we are talking about polarity, so polar and nonpolar bonds. By the end of this video, you should be able to identify a polar bond and also draw a net dipole moment on a polar bond. So the timeline of today's lesson is that first we need to understand what polarity even is. What is a polar bond? What is a nonpolar bond? What are these dipole moments that I just referred to? That's kind of a weird word. And then we're going to practice those words by applying the polar and nonpolar concepts that we're going to learn. So just a few seconds ago, before I hit record, I put a simultaneous drop of water and a simultaneous drop of acetone on a plate. And I'm going to show you that plate in front of me now so you can see what that looks like. You can see that there is a clear drop of water and the acetone drop is kind of like spreading out a little bit. Looks like it's still there. So if we observe these drops, the drop of water and the drop of acetone, over time, we should see something happening. So let's speed this up and see what happens. And as you can see now, after a short period of time, the water droplet is still holding together as an actual drop on the plate, and it's still there, and the acetone drop is gone completely. Where did it go? Where did you come from? Where did you go? Why is it gone, but the water is still there? It's in the same temperature bedroom. It's in the same area. It's on the same plate. Why is it that one chemical is still there and the other chemical is gone? What happened? That conundrum is exactly what we're going to be talking about in today's lesson. Polarity in chemistry means that there is an unequal sharing of electrons between two atoms. So if you have, like in this picture above my head, if you have oxygen and hydrogen, oxygen is indicated here in red and hydrogen is indicated in white. Basically what you have is that oxygen is like, my precious, and it's taking the electrons from hydrogen, or it's like holding on to them. It's not fully taking them, it's not stealing them. As you can see, they're both still kind of holding on to those electrons, those negative charges, and they're tug of warring them. But oxygen is so much more powerful, it's so much more electronegative than hydrogen is, that it is holding on to them or attracting them more strongly than hydrogen can. So we can say that oxygen is really attractive in this bond here, and there's an unequal sharing in that oxygen gets the electrons a lot more than hydrogen does. For hydrogen. You can also think of this from a previous lesson where we were talking about the tug of war between a Chihuahua and Arnold Schwarzenegger. This is the exact thing we were referring to in the lesson that comes up right there on the little info card if you're interested in learning about the tug of war between Chihuahuas and Schwarzenegger. So what periodic table trend is this? What are we talking about? In that previous video, we looked at ionization energy, we looked at electronegativity, we looked at a lot of things. We looked at levels, groups, etc., etc. Which trend is this? Hopefully the word that's coming to your mind is electronegativity, and you would be correct. This trend that we see of an unequal sharing of electrons, or polarity, is because you have a more electronegative atom attached to one that's less electronegative. Basically, the idea here is that the electrons are biased. They prefer to hang out with the more electronegative atom. That tends to be the popular kid, That's who everybody wants to hang out with. And everybody, I mean all the electrons, want to hang out with the electronegative atom. So as a reminder, if you don't want to go back and watch the whole previous video, who is more electronegative? So the trend for electronegativity goes across the periodic table, where it's least electronegative down here in this bottom corner, and it becomes increasingly more electronegative as you go this way across. Hopefully you can recall that fluorine is our most electronegative atom with a value of 4. It doesn't get more electronegative than that. So fluorine is the smallest kid on the block, but also the most popular. All the electrons want to hang out with fluorine. So if we're thinking about electronegativity in terms of metals and nonmetals then, you can see I've outlined this periodic table very horribly, I might add, but come on, don't judge me. It's with, I don't know, paint on the computer and a mouse. I'm much better with a paintbrush than on a computer. Come on now. So if we're looking at the metals here, the metals are outlined in blue, and the nonmetals are outlined in red. So in general, when we're talking about electronegativity, those who are more electronegative happen to be the nonmetals in comparison to the metals. So now if we were going to compare two specific different elements, if we were going to look at potassium being right there and oxygen being over here, between those two atoms, who is more electronegative? In other words, who do the electrons want to hang out with more? In this case, it would be oxygen. Oxygen is more popular than potassium. So if there was a bond between K and O, then what we would see is that the electrons would want to be around O way more than they want to be around K. They want to hang out with O more. So let's compare another two groups. How about a noble gas or a halogen? Which one of those would be more electronegative? If you recall, the halogen group is right here, and the noble gas group is all the way on the end. Now, the whole premise for noble gases is that they're noble. They don't need anything else. They don't need extra electrons. They're stable. They don't bother mingling with the common folk, whereas the halogens are only one electron away from obtaining nobility, and they want to be noble more than anything else. They're desperate for it. So, between those two, the halogens are definitely more electronegative because they're going to attract electrons desperately, whereas noble gases couldn't give a rat's patootie whether or not they got more electrons from another atom or not. They don't want to react with anybody else. How about alkali metals or halogens? This is again comparing two different groups. Our halogens are over here, and our alkali metals are over here. So who would be more electronegative between those two? If we were following that same trend where it's less over here and more over here, we'd have to then assume that the halogens are more electronegative than the alkali metals, meaning that the halogens are going to hang out with electrons more than the alkali metals are, or the electrons are going to be attracted to halogens a lot more than they are attracted to alkali metals. So then what is a polar bond? A polar bond is when we take two different electronegative atoms, just as we've compared those two different groups, who was more and who was less, and we stick those two atoms together. And if those two atoms share electrons unequally, there's an unequal tug of war, like between a Chihuahua and Schwarzenegger, we would call that a polar bond between those two atoms. There's an unequal sharing. So if you see the GIF above my head, you can see that the electrons will travel around hydrogen, but they spend way more time buzzing around oxygen. They are more attracted to oxygen than they are to hydrogen. This would be an example of a polar bond between an O atom and an H atom. How about an HCl? HCl is right behind my head, indicated in red and blue. HCl has two different atoms. Hydrogen is on the left side of the periodic table, and chlorine is on the right side of the periodic table. According to our trend, where it increases going from bottom left to top right corner, we would then say that chlorine has more attractiveness for electrons than hydrogen does. Chlorine is the sexy atom between the two, and the electrons want to hang out with chlorine a lot. So, what happens then is that those electrons are going to spend more time with chlorine, and if electrons are spending more time with you, they are intrinsically negative. That means that that side where there's more electrons hanging out becomes slightly negative. That's what this weird symbol is behind my head. That little cherry looking thing and a negative, that means slightly negative. So it's just a little bit negative because electrons are still moving. They're not stuck to chlorine, but they spend more time with chlorine than with hydrogen. So here's my analogy for you. If you were going to look at a polar bond in terms of where you spend more time, where you're more attracted to, or where you end up spending more time just overall, this would be an analogy for me. Between the kitchen and Netflix, I spend a great deal longer in the kitchen than I do on Netflix, on average. So in the kitchen, if I spend 2 hours, that atom I have indicated as red. I'm spending more time in the kitchen than I am on Netflix. So if I'm only 1 hour on Netflix to watch my show, right now we're watching The Blacklist, and we're in the last season that just posted on Netflix. And yeah, I'm just saying it's really, really good. And if you haven't seen The Blacklist, I love it. It's awesome. I love that show. I'm hooked right now. So yeah. Anyways, so if I'm 2 hours in the kitchen and I'm only 1 hour on Netflix, for every 2 hours that I spend cooking in the kitchen, which location is more electronegative? In this case, where I spend most time, if I were an electron, then the kitchen would be more electronegative than Netflix would. So since electrons, as I mentioned before, are literally negative particles, they are themselves little negative balls of energy. Where they spend more time becomes a slightly negative place. So the longer I spend in the kitchen, the more negative I become in the kitchen. I'm sure you can relate if you've been stuck in the kitchen for a long time. So what I would do is draw a slightly negative symbol next to the kitchen location. Like so. So this slight negative, which again you can kind of draw it as a 6 and then sort of curve the tail, or I like to draw it like this. You kind of start like this and then go around. I know it looks awful, but you know, you do you. That little cherry looking thing is your slightly, that literally translates to slightly negative. So you could even say that Dakanta is slightly crazy. You know you like that one. Where there are less electrons hanging out becomes slightly more positive. So if all the electrons are hanging out in the kitchen, all me spending all my time in the kitchen, where it's becoming more and more negative the longer I hang out in there, then Netflix is becoming a slightly more and more positive option for me to want to go do instead of standing on my feet cooking. I'd rather go be watching The Blacklist. So that area, Netflix, becomes slightly positive. And we show that with our little cherry, our little slightly, and then a positive symbol. So now, inevitably, even though I am going to watch Netflix for my hour, inevitably I am going to go back to the kitchen to get a snack. So even though I have to travel to Netflix, I have to go to my couch at some point and end up watching The Blacklist for as long as my husband can physically stay awake, because I would probably binge watch it if he allowed me to, I'm gonna go back to the kitchen to get a snack. I'm gonna go get some chocolate covered raisins or whatever. So inevitably, I travel back to the kitchen as the electron. So the arrow that I have now drawn between the two circles, between the two atoms, is showing the direction that the electrons are flowing to. So even though I do end up going to Netflix, I am still going to travel back to the kitchen more often. I'm going to stand up more than once to go to the kitchen. I'm going to have to refill my water bottle. I'm going to have to go get some more snacks. I'm going to have to throw out some trash. Whatever it may be, I'm going to be making multiple trips to the kitchen from my couch. So in this case, if I'm an electron, I'm going to show the direction of where the electrons are traveling to. And they are going to want to travel to the area that's slightly negative or more electronegative. So if we're going to use the same logic, let's try and draw some slightly negative and slightly positive symbols over a different molecule. This is a molecule of hydrofluoric acid. We need to compare the two atoms and see if there's a difference in electronegativity. In order to do that, we need to pull out our periodic table. If we think back to our periodic table, you should remember that the basic shape is something like this. And hydrogen would be on this side, and fluorine is over here. Now we remember that the trend for electronegativity is increasing, going towards fluorine. And hopefully you remember that fluorine is in fact the most electronegative atom out of all of the periodic table. So who do the electrons want to spend more time with? They are going to want to spend more time with fluorine. In fact, that's what these dots are indicating. The electrons, they're hanging out with fluorine. That's where they want to be. So in this case, the fluorine is going to be slightly negative. And where the electrons are not hanging out, where they're not attracted to, is becoming slightly positive. Excellent. That's how we would draw our slightly positive and slightly negative on an actual molecule. So now dipoles. What is a dipole? A dipole is specifically indicated by that arrow we drew. I drew an arrow going from Netflix back to my kitchen. The arrow is showing the direction of where the electrons are going, or showing that there's a difference between a slight positive and slight negative region on a molecule across a bond. So we always draw a dipole by using an arrow along the bond between any two atoms, and we're always going to have the arrow part pointing in the direction of where the electrons want to go. There's also going to be a positive butt end that's going to be on the slightly positive side of the molecule. So if we look at HCl right here, we can see that this is the dipole arrow. From before, we have to do the same thing. First identify who is slightly negative and who is slightly positive, which we do by looking at the periodic table and thinking about our trends for electronegativity. When we look at the periodic table, we see that chlorine is much more electronegative than hydrogen. Therefore, it is slightly negative. Then we're going to draw an arrow in the direction of where the electrons want to be. We know that they want to be with the more negative atom. That's the more attractive or sexy atom, if you will. So the electrons are going to go towards chlorine. Now we just have to add a little plus sign on the butt of our arrow to indicate where the electrons are not spending as much time. You can also see the dipole arrows here. There's more than one dipole arrow for boron trifluoride because it's between each atom. It's between the boron and the fluorines. And we know that fluorine is much more electronegative than boron because fluorine is the most electronegative atom on the periodic table. Therefore, it will always be the one that is slightly negative. When you draw dipole arrows, make sure you do draw them along the bonds. So you wouldn't want to do this. That doesn't make any sense above this molecule up here. You want to make sure that you're drawing those dipole arrows along the bonds, each individual bond. Let's try it for these molecules here. We're going to draw in our dipole arrows for the following molecules. The first thing we need to do is figure out who is more electronegative between each bond. Let's start with the one on the left. We have carbon and chlorine. Between those two atoms, who is more electronegative? If you look at your periodic table, you'll see that chlorine is farther to the right than carbon is on the periodic table. You can also see another dead giveaway here is that chlorine has these dots around it. Again, those dots are indicating electrons. We'll talk about Lewis dot diagrams at a future lesson, and you'll understand why those dots are there. So between carbon and chlorine, chlorine would be slightly negative, whereas carbon would be slightly positive. That's not the only bond we have, though. We also have carbon and hydrogens. Well, between those two, carbon would be more electronegative than hydrogen would, but in this case, we're only really caring about the huge difference between the more electronegative atom and the carbon. The reason for that is because carbons and hydrogens are nonpolar, which we will get to in a second. So hold on to that thought. If you're going, wait a second, why don't we care? Hold on to that. We're going to talk about nonpolar bonds next. However, for this molecule, we're going to draw our arrow in the direction of where the electrons are going, and then we're going to put a plus sign where they don't want to be. So a plus sign on the butt of our arrow right there. That would be our dipole arrow or our dipole moment. Now let's look at the next one. We're looking at ammonia. So for this molecule, we need to identify who is more electronegative, N or H. In this case, it would be N. Slightly negative would go on N because the electrons want to spend time with N, and slightly positive would go on H. In this case, we're going to go this way with our arrow because the electrons want to be on N. And we're going to put our plus butt right over hydrogen. We have other bonds that are the same, so we need to do the same for the other NH bonds. These H's are also slightly positive, and they also have dipole arrows that point towards the N, where the electrons want to be. All right, I promised you we'd talk about nonpolar bonds, and here we are, sure enough, talking about nonpolar bonds. If polar bonds are when you share electrons unequally, a nonpolar bond would have to be a bond where electrons are shared equally. So this would be like a tug of war between two Schwarzeneggers or between two Chihuahuas. It's a canceling effect. There's no tug of war between the electrons because each atom has the same electronegativity, or roughly the same, and so the electrons spend equal amount of times with both. The times that this occurs whenever we have a nonpolar bond is if we ever have two of the same atoms. So if we're looking at Cl2, so Cl, two Cl's attached to each other, a diatomic molecule. That diatomic molecule of chlorine is the same electronegativity on both sides. So they can't possibly out-tug of war each other. It's like a clone tug of warring with a clone. They're going to cancel each other out. It's a nonpolar bond. Those electrons are shared equally. Another time that we have nonpolar bonds is whenever we see carbon and hydrogen as a general rule. So anytime carbon and hydrogen are connected to each other via a bond, they're always going to be nonpolar. So carbon and hydrogen are sharing those electrons equally whenever you see them attached to each other. In other words, you can think of carbon and hydrogen as being really wimpy at tug of war. They just kind of stay stagnant. The third and final way that you can get a nonpolar bond is if two vectors cancel out. So flashback to physics, if we have vectors, i.e. our dipole moments, those dipole arrows we've been drawing, if two dipole arrows are the same and they go in opposite directions, then they cancel each other out. Just like if you had two chlorine atoms or two clones playing tug of war. They're going to cancel each other out in that regard. So the way you can think about this, coming back to my previous analogy, is that for a nonpolar bond, the electrons are spending equal amounts of times in both places. So if I was just planning on binge watching Netflix all day, any other activities I had planned on doing will just cancel out entirely. So in this case, I might have electrons going this way, and I might have an equal amount of electrons going this way, and my tug of war is essentially nullified. I don't get anything done. I'm binge watching Netflix all day, so I would remain stationary on my couch doing nothing. Likewise, electrons that are traveling about a molecule or across a bond, in terms of a nonpolar bond, are always going to cancel each other out if they distribute themselves equally on both sides. So here's the blast from the past, your physics past. If we were going to draw a resultant arrow for the following addition problems or subtraction problems, I know physics is going to haunt you forever. You thought you were out of it now, right? Nope, it's here. It's still here. So if we have two arrows pointing in the same direction and one has a value of 3 and the other has a value of 7, then our resultant vector or our resultant dipole would be that much larger and it would have a value of 10 because we're just adding those two together. However, if we flip two arrows around and we take a 10 arrow and we point it at a 3 arrow. So we have something going this way with a value of 10 and something this way with a value of 3, then what you get is still a value of going forward that's less, but only of 7. So 10 minus 3 is 7. The overall movement is still going that way because 10 is greater than 3. So it's still pushing the whole thing to go that way, right? If we're looking at up and down, you could also do side to side, either way. But they're the same value. So 4 going up, 4 going down. This is a case where they cancel each other out to 0. Nothing. I.e. a nonpolar bond. So when you have two dipoles that are pointing in opposite directions with the same values, then you have 0. You have a nonpolar bond. A key thing to keep in mind here is that this is uneven electron distribution, not movement. So unlike physics, where physics is talking about vectors moving, we're talking about cars moving or objects moving, we are not assuming that the whole molecule is like moving in one direction. It's in terms of the electron distribution, where the electrons are going, not the movement of the whole molecule. Again, remember that dipoles are just showing where the electrons prefer to hang out, where they want to be. They want to be around the popular kid, and the popular kid happens to be the electronegative atom. All right, so let's come back to this analogy again then. What about a nonpolar bond? How would that look in our analogy buildup? Basically, I want you to think about me trying to sandwich watching Netflix in between a whole full planned day of cooking. So if I was just planning on cooking all day and I was trying to watch The Blacklist or whatever cool show you like to watch on Netflix as the electron, am I really going to enjoy watching Netflix? Am I actually going to get to enjoy the show? And the answer is no, I'm not. I'm going to be spending all my time in the kitchen paying attention to not chopping my fingers off as I cut vegetables, as opposed to being involved with the show and the content that I'm watching. So in this case, my time is being tugged in opposite directions. You can kind of think about it that way. From an electron's perspective, I'm being pulled in opposite directions with the same force, just like the vectors we talked about earlier. So what I'd like you to envision is the more electronegative atom being the kitchen in this case. So I'm going to point my dipole arrow towards the kitchen and add a plus on the butt. I'm going to do that for the other side as well. Hopefully this looks familiar to what we just did with vectors. They are about the same size. I apologize, my drawing isn't that great on the Surface Pro, but the vectors are about the same size and they're pointing in opposite directions from each other. In this case, the vectors are going to cancel out. So the bond that we're looking at here for the molecule overall is 0. There is no net dipole moment. So this is where it can get a little tricky. I do have two dipole arrows. So I do have a dipole here and I do have a dipole here. However, for the whole molecule, for this whole molecule right here, they have canceled out. So overall, I have a net dipole moment, that's what we would call it, a net dipole moment of 0, because my vectors or my dipoles cancel out within the molecule itself. those electrons are technically shared equally on either side of the molecule and not just positioned on one side or the other in a greater concentration. So even though this molecule does have polar dipole arrows, just because we have dipole arrows doesn't necessarily mean that the whole molecule has to be polar. You have to check and see if there's any other dipole arrows that could cancel out the ones that are present. In other words, we can have polar bonds, but an overall non-polar molecule. A real-life example of this would be CO2, carbon dioxide. That stuff that you breathe out every time you breathe, and that gives plants their CO2 so they can give us oxygen. The circle of life. So we have CO2, carbon dioxide. It has something that is slightly negative. Oxygen is the more electronegative atom between oxygen and carbon. So it's the one that is slightly negative. And carbon would then be slightly positive. We're going to draw our dipole arrow towards where the electrons want to be. And likewise, we have another bond down here between carbon and oxygen. Oxygen is more negative than carbon will be because it's more electronegative. So we're going to draw a dipole arrow that way. Those two dipole arrows cancel. We have polar bonds within CO2, but overall the molecule is nonpolar. All right, let's come back around to this net dipole moment jazz. So if the dipole arrows cancel out, we have an overall nonpolar molecule. That means that the dipole moment is zero or no net dipole moment. No dipole moment at all, net, overall. If the dipole arrows are additive, however, so they're pointing in the same direction, we do have an overall polar molecule. So the reverse of the nonpolar one. Then we could say we have a net dipole moment. An example of that are these two pictures right here. And the first one being CO2 that we just talked about. CO2 has those two dipole arrows that cancel out. They are of equal magnitude in opposite directions. Here we have no net or overall dipole moment. It's zero. However, for H2O, we have slightly negative for oxygen, slightly positive regions for hydrogen, and we have two dipole arrows that are pointing towards oxygen. That means that overall, if we were going to add those vectors, if you remember from physics, you would put one vector and then you'd put the other one on the butt of the other vector, and then this would be your resultant vector. So the overall dipole moment. And that's where this arrow comes from down there. That's your overall dipole moment or net dipole moment pointing in that direction. So all of the electrons want to hang out with oxygen on a water molecule, essentially is what that's saying. So again, one thing that I saw a lot of students trip up on with this material is this concept above my head. So please write that down. Please repeat that to yourself. Even if a molecule has bonds that are polar or has polar bonds, the whole molecule itself can be nonpolar overall if those vectors cancel out. So please do keep that in mind. That is an important distinction and does tend to trip up a lot of people as they're first learning this content. Let's give it a try. We'll put this polarity thing to the test here. Let's try the first one. We've got carbon tetrachloride. Carbon tetrachloride. There are 4 chlorine atoms around one singular carbon atom. And what we want to do is analyze each bond individually. So first, which one is more electronegative, carbon or chlorine? You'd have to look at your periodic table in order to distinguish that. And you should be able to see that chlorine is farther to the right than carbon is. It's also a halogen. So halogens are one away from noble gas. They are pretty freaking electronegative. So chlorine in this case is going to be slightly negative and carbon is going to be slightly positive. We can write slightly negative for all the other chlorines as well. It's the same trend all the way around. And now we can draw in our dipole arrows. Notice that I drew all my arrows pointing towards the direction of where the electrons want to be, where they would like to be. All right, so if we were just looking at this flat model, of course, Molecules are not flat in the real world. They are 3D, so they do take up a little bit of a different space. Think about those orbital shapes in the last video. If you haven't seen that video, please do check out that with the little info card that'll pop up there. And see that the shapes do come out at you, 3D space back away from you, just like balloons. So in this case, we're looking at it flat. For this flat model, do all of those vectors, do all of those dipole arrows cancel out? And hopefully what you're seeing is that, yeah, these two would cancel out with each other, and then these two would cancel out with each other. So in this case, we would definitely say overall non-polar. All right, let's check out the next one. So how about boron trifluoride, the one in the middle? The one in the middle, we're going to look between boron and fluorine for our answers of which one is slightly positive and which one is slightly negative. Hopefully you've picked up from this video that fluorine is exponentially more electronegative than all of the other atoms on the periodic table. So because of that, we're going to say that fluorine is the negative part in this relationship. So fluorine is going to have our slightly negative, and boron, in this case, is going to have our slightly positive. We're going to draw our dipole arrows, always pointing in the direction of where the electrons would like to go. And they all want to go towards fluorine, away from boron. We're going to put positives on the butt ends of these arrows, and voila, we have some dipole arrows. We do have polar bonds in boron trifluoride. However, now we want to see, do these cancel out? I'd like you to think about somebody pulling on your back and another person pulling on your arm. Maybe it's kind of hard because it cuts off my arms here, but if you wanted to think of somebody pulling on your arms at kind of like a diagonal, and we were looking down on you. So let's assume you were standing right here and there's someone pulling at your back. So this is your friend right here pulling on your shoulders, and these are your other two friends over here pulling on your arms. If they were all pulling with the same exact strength, the same exact magnitude, would you move? Would you be disturbed? No, the answer is you would remain stationary. They're all pulling you in exactly the right angle to where your body doesn't move. Your body is just kind of stuck right in the middle. Likewise, with this boron trifluoride, these vectors do end up canceling out for the way they are angled against each other, kind of like the fidget spinner of the molecular world. So in this case, since this fidget spinner has all of its vectors, its dipole arrows cancel out, overall boron trifluoride would be labeled as a non-polar molecule. All right, we've got one more to go. How about the last molecule? The last molecule shows a bond between oxygen and carbon, and that's the one we're going to focus on. Between oxygen and carbon, oxygen is the more electronegative atom, so we're going to put a slightly negative, and then on carbon we'll put a slightly positive. So between those two, the electrons want to hang out with the electronegative atom, so all the electrons think that oxygen's pretty sexy, so they're going to go towards that oxygen. We're going to put a plus on the butt right by the carbon. And then what we can see is that we have one singular dipole arrow in this molecule. There are no other dipole arrows to cancel this one out. So that means that overall, this molecule would have to be polar. So here's a throwback to my video of will it dissolve? Will it dissolve or not? Where we were checking out whether or not a tooth would dissolve in Coke and vinegar and acetone and water and oil and all these other kinds of different things. If you haven't seen that video, please click on the little info card and check it out. It's pretty cool. One of my first ones. Pretty proud of it. So we discuss in that video how likes dissolve likes. So there's this trend in chemistry where if something is like another thing, those two things tend to dissolve in each other. This is what we meant by likes dissolve likes. If two things are polar, then they dissolve in each other, they mix. If two things are non-polar, then they also dissolve in each other and they mix. However, if they are different, if one is polar and one is non-polar, then they don't mix. They can't mingle. So this is what we meant when we first referred to likes dissolve likes. In the case of oil and water, like the picture right there, Oil is a non-polar molecule overall. It's made up of a lot of carbons and hydrogens. So oil being a fat and non-polar, whereas water being polar, which we discovered earlier, that was our H2O, and we saw that it did have a net dipole moment pointing straight up. So we know that water and oil don't mix because water happens to be polar, but oil happens to be nonpolar. They're not the same. However, Kool-Aid, or primarily sugar, is polar, and so is water, and that is why Kool-Aid and water would mix together. They're both polar. Now you should be able to test yourself and see if you can identify the slightly negative and slightly positive areas on both water and acetone. Those are the two chemicals that we began this lesson with on the plate. And I want you to check out which one might have or not have polarity. So maybe it has polar bonds, maybe it doesn't have polar bonds, maybe one is nonpolar, the other one isn't. Go ahead and draw in your slightly negative and slightly positive. Draw in your dipole arrows. Check to see if the molecule overall is polar or nonpolar, and maybe that can help you explain why one chemical was gone in a matter of minutes while the other one was still on the plate. The answer is to follow. Please click on the answer in the description below if you are interested in knowing if you did this correctly. And until then, wishing you a ducky day. Please like and subscribe. Thanks.
No ducks, no glory.